Hi everyone. So I'm Jonathan Simmons. I'm head of data science at Ordnance Survey, and I'm co-presenting today with Charis Doidge. Charis, do you want to introduce yourself?
Hi everyone, I'm Charis Doidge. I'm currently a data scientist at Ordnance Survey and currently on secondment for the government.
So our presentation is about that challenge of bringing geo to data science versus bringing data science to geo, and how we might tackle it. So we thought that to help us with this topic, we might use a bit of a character. Here's our example data science, and I think we gave him a name, didn't we, Charis? What was he called?
Yeah, Eric. This is Eric.
Eric. So Eric is going to help us through this thorny issue. So he's got a bit of a dilemma as to what type of data scientist he is. So perhaps he's one of those statistical thinkers. So he's statistically minded. He sees every data problem as a statistical problem. It's all about, trends and stats. Or is he a geographically minded thinker? Is he one of those people that just wants to put everything on a map and just think of everything as a geographical problem? Or is he one of these unicorns that actually can do everything? He do the statistics, the geography, the lot. And I suppose that's where we'd love to get everyone to, really. So yeah, that's the subject of this presentation.
So let's dive into one of these mindsets more. So let's start with the statistical thinkers. So usually they're coming from a statistics, mathematical, analytical background. Every problem they face, they're going to think of as a statistical problem, right? They're going to work with data and lists and tables and spreadsheets, something tabular, often something with columns or from a database. And when they're asked to visualize their results, they're going to put it in a graph, right? It's going to be a scatter plot or a line graph or a bar chart, something in Plotly, something in Excel. And often when they're talking about what they're doing, they're going to quote a lot of statistical mumbo jumbo when they're presenting everything, which half the room is going to understand and the other half is just going to have to pretend to. I think most data scientists probably fall into this category of statistical thinkers.
And then, of course, there's the geographical thinkers, which we should see in a minute. And these are the people who see everything as a geographical problem. So they tend to think of every data problem as a geographical problem wherever possible, tend to work with data in databases and also geospatial data formats, and often choose to visualize results on a map wherever possible as a first port of call. And we geographical thinkers loves to quote geographical mumbo jumbo when we're presenting our findings too.
So which one is better? Well, neither. What you really want is the best of both worlds. You want to have that one statistical eye and that one geospatial eye, so you can really make the best of your data and how you're going to present it. So this presentation, as we're from Ordnance Survey, is obviously going to try and convince the statistical thinkers to become more geographical. We totally accept the fact that going the other way round is totally viable, but it's not the point of this presentation.
So what's the challenge with geospatial data? What is it that makes it special and a bit quirky? Well, geospatial data files are often in strange and difficult to use formats. For example, the data is often split up into, say, tiles or lots of different areas, and that can make them difficult to work with. Then you often need special loading software to compile that raw geospatial data into a usable form. Actually, getting that raw geodata extracted, transformed and loaded is often really time consuming because the data volumes can be very large and difficult to handle. And then actually users very often have to obtain huge data sets that can be very complex and contain a lot of information just to access one particular element of interest. And actually specialist geo knowledge is often required to load and use the products. Now, we should remember that lots of geospatial data was originally captured and designed for cartographic display, not for analytical usage. That makes it quite challenging to work with for analysis. And so geospatial data sets often contain quirks. They often require workarounds and additional steps to be undertaken before they can be used for that analysis. And the overall experience for the new user can be confusing and frustrating. So therefore, we feel that the barriers to getting started are set pretty high. So how can we overcome them?
So we are proposing today 2 approaches to try and put more location data in the hands of statistically minded people. So the first is the obvious one, right? Develop and promote some geospatial tools and techniques. Get people thinking about geospatial in the data science community. Give more skills and tool sets to them so that they can do this themselves. The second one is slightly more interesting, which is, why don't we start transforming geospatial data into more simple, usable metrics that work with existing tool sets, perhaps things like CSVs or tabular data, things that people are used to using. So we're going to present both of them to you today, and I guess it's up to you to decide. So approach 1, how do we develop and promote geospatial thinking in the data science community? So I would suggest there's 3 things that we need to be thinking about here. One is the geospatial tools that are available to you. One is the geospatial data that's out there and available in the ether. And the other is how you're going to visualize that data. So let's start with the first one, geospatial tools. So libraries are really going to help you out when it comes to doing any sort of coding around geospatial data. There's things like Apache Sedona, which are great when you're doing it in a Spark or cluster sort of environment. You've got things like Shapely, which will just work off the bat on shapefiles in Python. You've got GeoPandas, which is a great example of where you can make that switch from being a classic data scientist to a geospatial data scientist, because almost every data scientist works in pandas, and it's exactly the same. It's just got a geometry column in it. And then there's also bespoke libraries like GeoMallet, which is one of Ordnance Survey's bespoke cluster Databricks-based libraries. So let's go into an example. On the right here, you can see a product that I output earlier this year. It was called Urban Area Polygons. And what we wanted to know was what areas of GB were urban and which ones were rural. So we divided the country into 50-meter cells, 50 by 50-meter cells into chunks. And then we had a look at the underlying topographic data to work out whether that was indeed an urban or a rural polygon. So things with lots of buildings in it, lots of roads, that's going to be urban. Things that are like grassy open plains, that's probably going to be more rural. So I went into our underlying topography, and I think we've got 500 million complex polygons in our database. So I ended up using GeoMallet. I pulled out all of the polygons that actually met the requirements, which you can see in yellow for being an urban polygon. And then I ended up with 20 million polygons, which were all overlapping each other and were super complex and difficult to handle. And we're talking terabytes of data here, complex data. So using GeoMallet, I had a dissolver in there, and I managed to dissolve those 20 million polygons in 2 hours, 40 minutes. I just had to check my notes there, make sure I'm not getting it wrong. 2 hours, 40 minutes, we managed to dissolve them all, which is incredible. We used to use a different tool for this, which was bespoke for doing geospatial data, and it would take a week to perform this task. So there's tools out there that are really going to speed you up, even when you've got hard data sets to use. And from that, we created the national data set in about 4 hours for the entire process, end to end, which is pretty good from a week. Let's look at another example. So in this one, you can see the red dots are our address points, and there's 1.7 million of these. And then you can see in the green and pink, we've got some play spaces, playing fields, and public park or gardens. And in the yellow is going to be our address of interest. And what we want to work out is how far away is the nearest green space in walking distance of this address in Southampton? So the actual answer is 280 meters, right? But if you didn't solve this in a geospatial way, you could probably approximate an answer, but it's not going to be as accurate as if you're using things like these geospatial libraries. So let's say we wanted to get a proxy answer and try to avoid the geospatial question. Maybe we'd reduce that polygon down to a single centroid where that blue cross is, and then we'd do a calculation. We could use something like scikit-learn, nearest neighbors, 2 points, what's the distance between them? But as we can see from this image, that's not really that accurate. It's about 100 meters off. And this is talking about quite a small park. If you had a giant park, if you're thinking like Hyde Park or something, that center point is not going to go very well. So let's say we still don't want to make that geospatial leap, But our data scientist is going to reduce that polygon down and just use some bounding, like more bounding box points. So they come up with these 4. Well, it's the same thing. One of those 4 crosses is probably fairly close to 280 meters. But again, if we were dealing with a huge park, or if you had a long, skinny shape, you're going to be really far away from approximating it. And then finally, there'd be someone out there who put a min-max bounding box around it, and we can already see how rubbish that would be, and totally wrong. So instead, if we solve this geospatially using something like Apache Sedona, I can use something like st-intersect after creating some radiuses around my points. I can use st-distance, and using an 8 cluster instance, I can get the answer nationally in pretty much an afternoon. And that's for the whole data set, by the way, not that one point. That would be terrible. So when we're also working with Databricks and we are working on a cluster level, why not go whole hog? So why not throw all of those 1.7 million address points in, but also let's turn on all of our bowling greens and cemeteries and religious grounds and golf courses. We can start to calculate the distance to all of these things in hours, which before would have been such a horrible, scary task to try and achieve. You'll actually see how this can progress later. We can do one better when we also start using routing instead of just birds flying distance. So this data set was actually used by the ONS recently. They were having a look at during times of COVID where people are being locked in, maybe having access to a park within walking distance if you didn't have a private back garden might give people, you know, a more sense of being outside and more health and whatever. So this has been used recently in that study. Okay, let's move on. Geospatial data. So it's really key that you get the data right. If you get the data right at the beginning, you're going to give yourself such an easier time with this. So some easy things to remember are there's some great data sets out there for GB and for the UK. In the ONS, they do things like the nested ONS geographies, which tessellate beautifully within each other as a hierarchy. You can use these in tabular CSV format and then just instantly plot it on a map. So this is like your first barrier is going to be use those ONS ones. They're pretty easy. You can just munch them into a column. The next thing is the OS Data Hub. I am from OS. I've got to give it a plug or my marketing team would be on me. So this is our Data Hub is access to open and premium APIs. You can get things like vector data, raster data, background mapping for free, linked identifiers, all the addresses and stuff like that. I believe you get 50,000 API hits for free. And also some of the products are free full stop. And actually, I've been using it since January and I still haven't hit my limit yet. And I have been using it every day. Other things are things like shapefiles, which we're more used to. That's more a classic way of showing geospatial data and also geodatabases. Things like Shapely will help you load those. Also things like GeoPandas will be able to handle them. Just make sure you check your coordinate reference system because it's the first thing that will trip you up. And finally, I want to talk about geospatial visualization. Now, this is a part of geospatial that has come on leaps and bounds in the last couple of years. It used to be that to visualize your data set on a map was actually like 10 or 20 lines of code that were really complex and difficult to use. But now I promise you the libraries will do the hard work. Things like Folium and Plotly are really easy to use out of the box. Things like Leaflet, you've also got ArcGIS Online that could be useful. And don't forget that when you visualize a data set, you're going to bring a whole new dimension and a whole new insight. So I was doing some clustering on socio-demographic and geographic data, and I had it at different levels in the ONS geography. So I was looking at LTLAs and UTLAs and all the way down. And I wanted to see how well those clusters were working. I did my normal quality control, I did my silhouette plots and whatever. But I had no real instance of where these geographical points were falling. So instead, I just plotted them on a map. And in the top left, you can see actually, this data is clustering quite nicely geographically. We've got all of London in one colour. We've got the outskirts of London in 2 different colours. And then the rural locations are coming out in yellow and purple. So as soon as you plot this on a map, you get this whole new insight to it. And you could do things like points, cartograms, choropleths, all just out of the box with these libraries. And finally, you can also build dashboards straight to this. If you're familiar with using Dash, you'll know that Plotly Dash work quite well together, as does Folium. You can link these dashboards live to your cloud data buckets. So it's really easy to use. They're all pannable. You can pan around, zoom in, you can select things. This is in a Jupyter notebook, by the way. You can just do this in a notebook format. You can select things and actually use your selections to then update the graphs around it as well. So I just wanted to give a push to these things, that they have come along so far recently, and they're really easy to use now. So what if this is still too much of a barrier to entry? What can the geospatial community do to try and make it easier for everyone?
So that's where the second approach comes in. And this is about transforming that geospatial data into simpler contextual metrics that work within existing data science toolsets. So for example, let's talk about addresses. An awful lot of data is captured at the property level against individual addresses in various different systems. Now, imagine that we could calculate simple metrics for each address to give it some geospatial context. That could then be referenced to a unique property reference number, as we have it in Great Britain, UPRN, a land registry title number, or whatever the preferred referencing scheme is for properties in the country you're working in. And actually, if you got the right unique identifiers against your data, of course, that then helps with linking it to any other data set by that unique identifier, or heaven forbid through address matching, which is also possible, but we like to avoid as far as we can.
As much as possible.
Absolutely, it's a nightmare. But what kind of metrics are we talking about at address level? So here's an example of some geospatial data around an individual property. Now, there's an awful lot of information hidden in there that is implicit. It's not explicitly there in the data until you do some geospatial calculations to extract it. So for example, from this, we can calculate that actually it's a detached property. It's not attached to any of its neighbors. It's got various different sizes. So you've got the size of the plot, the size of the building, whether there's a front and back garden, whether there's sideways, is there a verge outside, pavement, the width of the road, neighboring properties, connectivity information, whether there's outbuildings, the height above sea level, the height of the building, how many floors, all that kind of thing could potentially be extracted from the underlying geospatial data and associated with the address and ideally the unique property reference number. And then, of course, we've got things like proximity. So actually, it's very common to want to know for each address, how near is it to certain services? Now, as Charis mentioned, you can do those distances as the crow flies to things like railway stations, supermarkets, airports, identify the nearest one to each property and the distance that it is away. But of course, there's also the road distance that actually is sometimes very different to the as the crow flies distance, as you can see there. And then there's all sorts of fairly standard repeatable examples that would be needed for lots of purposes. So the distance to schools, primary schools, secondary schools, doctors' surgeries, emergency services, all that kind of thing could be pre-calculated for every address just once, and then shared in a very simple, easy to use tabular format against those address level identifiers. And then what about area-based summaries? So obviously not everyone has data that's at an address level. Sometimes people work at postcode level or administrative or statistical geography level. But of course, you can summarize that data, geospatial data at these levels as well to give some geospatial context to these things. So we know that a lot of companies create aggregate data at postcode level and then want some geographical context for that data. Now, of course, you could, like as with the addresses, summarize data into metrics against postcodes to provide that. So here's an example of another kind of standard geography, grid squares. So, for example, if you're a mobile phone operator, you might have divided the country into 100-meter grid squares, for example, and have various telephony data or telematics data against those grid squares. Now, actually, wouldn't it be nice if you could actually then find out what that means? So grid squares have fairly well-known identification systems. You can count things like the number of residential, commercial addresses, the proportions of different types of land, the presence of things. So is there a supermarket in that grid square? Is there a park? You know, just that yes, no answer is really useful.
Or is there a pub?
Yeah, absolutely. Is there a pub? You know, and postcode data as well. So you can do a very similar summary there. You can count the addresses, you know, the presence of things, the sizes of gardens. And as you can imagine, this kind of data has been very sought after and useful during the COVID-19 pandemic response, you know, actually wanting to put geographical context against various data sets at postcode level has been really valuable. So then statistical geographies. A lot of us will be familiar with those in the UK. We have the most granular data available at output area level. And then there's a nested hierarchy of geographies going through two types of super output area up through wards and local authority districts and right up to country level. And that's a brilliant way if you want to be able to map geographical context to census data, for example, and other national statistics. And then there's the different types of summaries that we're talking about. So of course, we talked about counts and breakdowns by type and the presence of whether something's there or not. But also you can do area-based analysis. So total areas of things, sums, proportions, averages, minimums, maximums, all those aggregate calculations can be performed at different area geographies. And then finally, ease of access is really important. So actually, we could be talking about an awful lot of pre-calculated metrics here, and making that all available within a simple, flat, maybe database-friendly structure and format is going to make it an awful lot easier for people to get up and running within existing tool sets. And actually, the use of unique identifiers to reference everything back to the appropriate geography is going to remove all the pain of address matching and name matching that we're so familiar with in the world of geo. And actually, wouldn't it then make it all a lot easier if you could then do bespoke downloads and obtain just the rows and columns that you actually need for a specific problem? So I think we've got an example of this on the next slide. So you should be able to filter things by just the attributes you actually want and just the geographies that you're actually interested in for your specific problem, so that it's all just there and ready to use within your system of choice. Oh dear, we've lost the slides. That's not good. But anyway, there was only one left, and it was a I've got them here. Which approach is the best approach? So Charis was going to summarize. In fact, she's back. So I think I will hand over to her to summarize which is the best approach.
Apologies, everyone. There we go. Is that it?
Yeah, you got it.
Fab, great. Okay, so in approach one, when we were talking about learning new tools and techniques and encouraging statistical thinkers to think geospatially, obviously you've got more flexibility that way. You've got no limits to what you can do. You can choose. You can pick and choose for yourself. If you've got better domain expertise, you're probably going to have better understanding of where your results are coming from. So, you know, better knowledge over it. If you visualize your data geospatially, it's going to give you new insights. There's going to be things that you may not have noticed before. And also, it's always good to add new tools and techniques into your wheelhouse. As data scientists, that's sort of par for the course and what we're expected to do. On the cons is, as that is what it's expected to do all the time, sometimes you're just learned out, and it is a lot to learn. The data does have a lot of gotchas, and some of them are quite tricky to solve. And also, the data is quite large and onerous, and therefore it's expensive to process often. You heard me talking earlier quite a lot about Databricks and clustering, and as we know, that all adds up. What about the other approach, where we condense crazy geospatial data down into actually easy to use metrics? Well, the pros of this is it's really easy to get started with. It's just point and click. It's going to be compatible with all your existing tools and all your existing data sets. You're just going to add them on. It's a really quick start to geospatial visualization and thinking. It's going to get you involved right at the start. And also, using tabular data means that there is no real geospatial barriers to entry. On the cons, I guess you're limited to what's available, what people have put out there, what's already been aggregated for you. And also you've kind of got a lack of control over what you're doing and a lack of understanding about the underlying calculations.
So in summary, which approach is best? And the answer is there isn't a right answer to that. It really is horses for courses, and it depends on the problem you're trying to solve, the level of accuracy and in-depth understanding that you require. And it really is horses for courses according to the situation that you're in. So are there any questions?
There are indeed. Thank you, Charis and Jonathan. Jonathan, you were cool as a cucumber when we lost the slides, and Charis there.
Don't worry, I didn't. Yeah, I didn't even notice, to be honest.
On virtual events. First of all, thank you for your presentation. It's because of we've lost Charis again. No worries. Must be some issues with the internet connection. Anyway, we have a few questions, and also lots of people are asking for the deck because they found the presentation so insightful. So thank you for that. But we have a question here from Gordon Linton, who says, how do you account for multiple dwelling buildings when working at postcode boundary level? For example, a high-rise block of flats or a mixed-use office residential complex? A nice specific question here.
Wow. Who wants to answer that? Do you fancy having a go, Charis, or do you want me to try?
Hang on, I've just found it in the chat. How do you have multiple dwelling buildings when you're working at? Okay, so actually for a lot of our buildings, even if they are joined, flats are slightly different, I've got to be honest with you, but we do actually capture property boundaries from each one, and we do know when they're multi-level, multi-residency occupation buildings. We have that as part of our address base as well, so we would know that there are 2 different address points that are falling within that building, so we could swap between which way it is. For flats, I don't know. I don't know as much about how we're going to capture that in our topographic data, I'm afraid.
Yeah, I think it's the same. Yeah, I think it's the same. So we know how many flats there are in a given building, and we know that postcodes sometimes duplicate each other. So sometimes there are multiple postcodes within one building, and of course, you know, you have to take account of that when you calculate these things. But yeah, essentially, I have no problem with lots of polygons that are building shaped sitting on top of each other, to be honest. So I think it depends on your problem again, and how you need to account for these things.
And the world is 3D, so maybe our databases should be too.
There is that.
Quote of the day for Twitter there. I like that one. We also have a question here from Norris, who's asking, at Ordnance Survey, what was the driver for the decision to use Jupyter over R and Shiny?
I think, honestly, most of it comes down to the fact that it's a lot of what our data scientists use, although we do have specialists in R and also Scala. Obviously, that's on an uptick because we're all moving towards that Databricks sort of clustering environment. I'll be honest with you, I think it's because it's what most people are comfortable with.
Great. Nice.
Yeah, it's the tool that was available to us.
I mean, R is fantastic. R is great, and it's great for visualization as well. And I think a lot of the things I talk about, you'll find an equivalent in R. So whatever you're comfortable in.
Fantastic. Well, guys, thank you so much for such a great presentation. There might be a couple of questions because some people have put them on the event chat rather than the stage chat, but because we need to move on to the next presentation, thank you so much for joining us. We'll be sharing this on YouTube for anybody who's wondering. And yeah, I think we will also share a PDF to the slides because I feel like this is a very practical one. People have wanted to take this back into their organization. So thanks so much for joining. Bye, Charis and Jonathan.
Fantastic. Bye. Thanks for listening. Bye.
Our pleasure.